Hi, my name is Dr. Steve Jessup, and this is the Weather Classroom on YouTube. This is the Weather Weenie activity number 1A, first in a series of a number of activities related to the weather for students in upper middle school, 8th grade, through high school, and even into college. We'll be talking in this video about weather balloon observations and time conversions. So what can you expect in this video? First, we'll talk about an introduction to weather balloon observations. Why are they important? How are they made? We'll be talking about the timing of weather balloon observations, how often we make them, and where we make them. And we'll be talking about time conversions. How do we convert from universal time coordinate time to local time? So weather balloons provide essential observations directly from the atmosphere. The data they provide is known as in situ data. In situ is a Latin term for in position. It means that we take that data directly from instruments that sense the atmosphere or the ocean directly. And so we have a weather balloon with an instrument package tied to it that is floating through the atmosphere. We have a thermometer or some other sensor that's dragged through the ocean that measures something properties of the ocean. Or we have weather stations which are on the ground that measure the weather as weather systems pass through and as weather conditions change. So consistent weather balloon observations in the United States date back to 1937, and now we launch weather balloons twice a day from 92 stations in North America and the Pacific Islands, and from 10 stations in the Caribbean islands, overseen by the National Weather Service of the U.S. Other national weather services or national meteorological organizations oversee weather balloon observations in other countries as well, and they're all synchronized together. We send up an instrument package known as a radiosonde if there is no wind observation taken, or a ray wind sonde if there is a wind observation taken. And this radiosonde or ray wind sonde is attached to a helium-filled balloon, and it transmits data back down to a computer on the ground throughout its ascent through the atmosphere. And then this computer records the data and saves it for posterity. The data received by the weather balloon flight is commonly referred to as a sounding or a Rayob. Rayob, of course, is just short for radio observation or radiosonde observation. This data is important for computer models that are used to forecast the weather. Computer models ingest the weather balloon data, okay, from a sounding or from a Rayob from the different sites, and this provides the initial state of the model, the beginning state of the model, and then that model is projecting forward in time, calculating how the weather conditions are forecast to change using various mathematical equations. And so here's a map of the Rayob sites across the continental US. There are also 2 in Hawaii, 1 in Puerto Rico, several in Alaska. And if you go to the link, you can also see the locations of the ones in Alaska and the Pacific Islands. But here you can see that the United States is blanketed with about every 300 miles or so, 300 to 400 to 500 miles, there's a radiosonde site across the country, all the way from Caribou, Maine to Key West, Florida, from Northwest Washington to Southern California. And you should be able to locate the Rayob sites closest to you by looking at this map. So what data do ray wind sondes collect? Remember, a ray wind sonde is the one that does collect wind data. So we collect height data, how high above the ground is the instrument package, what is the pressure at that level, what is the temperature, what is the dew point or the moisture content of the air, how much water vapor is in the air, what's the wind speed, and what is the wind direction. And then this data is plotted on a special diagram. Okay, and in general, they're called thermodynamic diagrams, but the specific name for the diagram that we'll be using is called a skew-T log P diagram. And we'll be working with these SKU-T diagrams, we'll call them SKU-Ts for short, in this video, and we'll continue to work with them for several more videos as well. We'll explain different parts of them, different pieces as we go through. But we'll get to the SKU-Ts in part B of this video. For now, we're going to talk about the timing of the weather balloon observations. Rayobs are taken twice a day, not just in the US, but around the globe. These observations are synchronized, okay? So at 0 and 1200 Greenwich Mean Time for Greenwich, England, we take observations twice a day. And GMT is also known as Universal Time Coordinate or Zulu time, so it has several names. You may see Z time on some of the websites that we use throughout the videos. And so if you're in a different time zone than Greenwich, England, which if you're in the US, you are definitely in a different time zone than Greenwich, England, you must convert your the 0Z and the 1200Z or UTC time to your local time by counting time zones, how far away you are from Greenwich, England, and adding or subtracting them from GMT. Okay, daylight savings time complicates things even more because then we're an hour off from standard time, and we have to convert for daylight savings time as well. We'll talk about that on the following slide. And then we need to be careful with evening and observation and nighttime observations with which date you select, because if it's 0 UTC, it may be 7 p.m. on the day before that where you are. Okay, so if you're looking to convert to UTC time, you have to be careful, especially in the evening and overnight hours. So here's a map of the world time zones, and you can see Greenwich, England, here's England, and the UK and Ireland, and you can see their time zone is labeled with a 0 because they are the standard time for the globe. Greenwich Mean Time is the global standard. And you can see in the eastern US, we are at a kind of a medium purple here, also down through Peru and Cuba. But in the eastern time zone, we're 5 hours away from Greenwich, England. Okay, minus 5 hours. If you're in Central Time, it's -6. If you're in Mountain Time, it's -7. And if you're in Pacific Time, it's -8. And here's a look at the 4 time zones across the United States. Okay, Eastern Time, Central Time, Mountain Time, Pacific Time. If you're in Alaska and Hawaii, you also have different time zones as well. So here is a couple of tables showing you time conversions from GMT to the 4 time zones across the United States. You can see that 0 GMT and 12 GMT give you the same time, PM and AM, across the different time zones. So in Eastern Standard Time, it's 7 o'clock PM when it's 0 GMT, it's 7 o'clock AM when it's 12 GMT. And then in Central Standard Time, it's 6 p.m. and 6 a.m., Mountain Standard Time, 5 p.m. and 5 a.m., Pacific Standard Time, 4 o'clock p.m. and 4 o'clock a.m. And then in Daylight Savings Time, EDT, CDT, MDT, and PDT, we spring ahead an hour, or spring forward an hour, and so we have 8 o'clock p.m. at 0 GMT and 8 o'clock a.m. at 12 o'clock GMT for the Eastern Daylight Time. Central Daylight Time is 7 o'clock, Mountain Daylight Time is 6 o'clock, and Pacific Daylight Time is 5 o'clock. So I hope you found this video useful. Be sure to like, share, and subscribe. Click the little bell to get notifications of when new videos are posted. And be on the lookout for part B to this, where we will look at SKU-T diagrams and interpret winds and pressure on the SKU-T diagrams. We'll continue working with SKU-T diagrams for a number of videos as we go ahead. And I hope you found this video useful and informative.